Our next compound to synthesize is luciferin. Luciferin is actually present in firefly. There are different analogs for luciferin, but here in this lecture, we are going to discuss the luciferin present in the firefly. So it's actually called the firefly luciferin. If you look into different literature, if you look into different sources, there are different structures, structural analogs possible for the luciferin. So to fixing a particular structure, we are choosing the firefly luciferin. That means the luciferin that we get from our common firefly. Some nights you can see some light is flashing around, and you can see that it's actually this compound is present there, and this compound is responsible for the color of the compound of the fireflies. And if you look into the structure of the luciferin, this is a big structure. Okay, it's having two heterocyclic ring. I can see that there is a good review written by Alexandra S. Sarakova. The title of the paper is Luciferins Under Construction, a review of non-biosynthetic pathways. The paper is published in an open access journal called Frontiers. You can see the link given below, or if you can just give the title of the paper in the Google, and you can see that you can download the paper and read the full content of the paper. So it's actually therefore an open access journal. And you can see that the structure of this luciferin, and I just want to give you a brief idea of the structure of the luciferin. You can see that this is actually, this part is called a benzothiazole unit. It's called a benzothiazole unit. So we'll be having here a benzothiazole unit. Okay, and here we are having a thiazolone unit. This is actually a thiazolone unit. Okay, so we can imagine the compound, okay, coming from three very important compounds. This is actually from benzoquinone part. This is actually, we can derive from benzoquinone part. This part we can derive from this part. Second part is actually we can generate from cysteine. Cysteine is an amino acid. Cysteine is an amino acid that contains thiol group. The thiol group. This is a CH2SH thiol group, and NH2 and COH. It's actually an amino acid. Okay, so you can get it from two. This part, the middle part comes from actually the amino acid cysteine, and this part also we can generate from the amino acid cysteine. Actually, what happens is that this luciferin, in presence of the enzyme luciferase, okay, in presence of enzyme luciferase, it takes oxygen. It takes oxygen and it spends ATP. Okay, and in presence of magnesium ion, what happens is that it will become oxyluciferin. What happens is it becomes oxyluciferin. Okay, it becomes oxyluciferin. Okay, this oxyluciferin compound can take light. Actually, can take light, and you can see that light can be used that take light and becomes excited state. Okay, and later what happens is that it comes back to the ground state by emitting light in this form of fluorescence. That is why we are seeing light flashing in the fireflies. At that time, it absorbs light. Okay, and the enzyme luciferase converts the firefly luciferin, takes oxygen and ATP in presence of magnesium ion and gives like that. It's actually what is happening there. Okay, now a lot of synthetic articles are being reported about luciferin, but for simplicity, I'm using this this paper. It's actually given by Meroni, Rajabi, and Sandinolo. The title of the paper is D-luciferin, derivatives and analogs, synthesis and in vitro and in vivo luciferase catalyzed bioluminescent activity. and is reported in the journal Archivoc 2009. I'm using this method to study the structure of a synthesis of the luciferin. As I told you before, there are a lot of varieties of luciferin, but we are restricting our discussions only into the analogs. Okay, that is present in the, not the analogs, but the analog that present in the firefly. That's why we usually refer that to firefly luciferin. Okay, this is the actual process of luciferin becoming oxyluciferin that I told you before, and it's not important for our point of view, but I just want to show you why this is happening. You can see that all biochemical reactions are the consequence of some synthetic, some chemical process happening in the body, and the firefly is also not an exception. Okay, so it's having around 9-step synthesis. Okay, it's having around 9-step synthesis. We'll going to start the compound from para-anisodine. You can refer to the paper and you can understand the more about the compound. This is called para-anisodine. It's para-anisodine. Okay, para-anisodine. Okay, what happens is that we're converting, we are adding, we are protecting actually, in fact, not we are protecting, but we're building a side chain. The H should be replaced by COET. Okay, for that we can make use of the reagent ethyl oxalate. By using the compound ethyl oxalate. Oxalic acid is COOH. COOH. Okay, and you can see that here we got ET. Okay, and actually here also we got H. Okay, is ethyl oxalate. What can happen is that here the H from here and the H from here will go to spartan. Okay, and we'll be getting this compound. The reaction will take place at 180 degrees Celsius. Okay, and it forms this compound. Okay, the step 1, the first step of the process. Okay, so that means there is COET group is introduced to the amino group of the para-anisodine, the first step. Okay, the second step, what we have to do is that the O should be replaced by sulfur. You know, our aim is to make sulfur and hydrogen in the same ring. Okay, so in the next step, what we do is that we have to replace the O by sulfur. To that, we can make use of P2S5 reagent. And we have to reflux by using P2S5. Okay, so here what happens is that the oxygen will be replaced by sulfur. You would treat with P2S5. Okay, the second step of the reaction. Step 2. This is the step 2 of the process. This is the actually step 1 of the process. Okay, and in the next step, what we had to do is that we had to remove the COOET. This we had to deesterify that. That means we had to hydrolyze the compound process. Okay, for that, first we can use NaOH. Hydrolysis, we can make this NaOH at 0 degrees Celsius, low temperature ester hydrolysis, and followed by, after that, we'll be getting a salt, sodium COONA. To remove that salt, we have to add HCl. That leads to the formation of this compound, compound number 7. Okay, this is actually the second step, but it's actually in the second step. Okay, and the next step is a bit complicated. The next step is actually, what we can say is that it is actually a bit complicated step, and what I will do is that I will write it in another step and come back. I will write the next step from here to here in the another slide, and after that we'll come back to this slide. Okay, so we have got this compound here. This is the compound that we have. Here we got O, Me. Okay, and here we have NH. There will be double bonds, and here there will be COOH. Okay, so I'm going to write them in another way. I'm going to write this compound in another way, like this. This we are having OMe, and its para position here we have got the NH. Here we have got the NH. Here we have got the NH, and you can see there is carbon, double bond sulfur, and to this we have got COOH. This is the compound. Okay, there will be some changes happening to the system. There will be some changes happen to the system. Okay, in presence of potassium ferricyanide. Okay, I'll write it again, the structure here. In presence of potassium ferricyanide, some changes will happen to the system. Here there is OMe. Okay, here we have got NH as we told before. There is carbon double bond sulfur. Here there is COOH. Okay, in presence of potassium ferricyanide, K3FeCN6. Okay, in presence of hydroxide, presence of base at low temperature. Okay, that means at less than 10 degrees Celsius. Less than the Celsius. Okay, what happens is that there will be cyclization. There will be cyclization. Okay, there will be cyclization. Let us see how the cyclization will happen. Okay, so here we can see that there is a carbon, this bond is there. This bond shifts to this place, and you can see that this bond goes to this carbon atom. You can see that already there is a hydrogen atom here. Okay, so there will be cyclization happening here. Okay, as a result of that, the cyclization, there will be OMe. Okay, there will be N. Okay, so what happens is that here the H will go to H plus, the bond shift towards here. Okay, so there will be C double bond OH here. Okay, there is sulfur. Sulfur adds to this carbon atom. Okay, there will be H here. And you can see that this electron goes to this place. Okay, there is minus H plus. Proton will go off. This proton will go off. Okay, now what happens is that because of that, this carbon atom will become negative charge. This carbon atom will become negative charge. Okay, that means the electron will be here. And you know, in the next step, what happens is that already an H plus is going off. Okay, now what happens is that this will come. This will go off, and it will give you this compound. There will be OMe. Okay, and you can see that here there will be nitrogen, double bond. Here there will be COH. Here there will be sulfur, like that. And as a result of that, what happens? H minus will go off. Earlier H plus went, here now H minus go off, and the H plus and H minus will go out as minus H2. Actually, in effect, what happens is that hydrogen gas is evolving out. The reaction will take place in presence of potassium ferricyanide. The reaction will take place in presence of potassium ferricyanide. Okay, thus we'll be getting the compound number 8. This is the compound number 8. Compound number 8. So you can see that this is compound number 8 that we are having. We get a ring like this. In the previous slides, I have discussed the name of the ring. It's called benzothiazole ring. So we got a benzothiazole unit as a result of this reaction. We got a benzothiazole unit as a result of the reaction. Okay. The next step, what happens is that we have to convert this COH to COMe to protect the group, because the group will be highly active. So what we have to do is that we have to protect this COH. Okay, for that, what we can make use of is that there are a lot of reactions that we can make actually in this process. Okay, so it's actually a methylation process, and we can make use of what reagent? It's a very simple reagent. We can make use of is diazomethane. We can make use of diazomethane. Okay, so this step we can make use of diazomethane, CH2N2. The diazomethane can be used. Because diazomethane should be at very low temperature, 0 degrees Celsius, that we make use of diazomethane. It will give methylated compound. Now we are going to convert this to an amide. Okay, so that means it can be done by heating with anhydrous ammonia. That will be done by using anhydrous ammonia in presence of methanol. We treat anhydrous ammonia in presence of methanol. What happens is that this ester group becomes an amide. This is actually an amide moiety. That becomes an amide moiety. Okay, that becomes an amide. So the reaction, the compound number 8 becomes 10, and the ester is converted to an amide here. The ester is actually converted to an amide here. Okay, now what we are going to do is that this amide, if it undergo dehydration, you can see if there's H2 and O in amide, H2 and O will be amide. Okay, if it can undergo elimination of water. Okay, it can be done by using POCl3. Phosphorus oxychloride, POCl3 is a good dehydrating agent. It removes the water. H2 and O is going out. Okay, and as a result of that, when H2 and O is going out, it becomes a cyano compound. It becomes a nitrile. That becomes a nitrile. The compound becomes a nitrile. Okay. The next step, what happens is that we are going to remove the OMe, anisodine OMe. We are going to convert to OH. We're going to convert to OH by heating that with pyridinium hydrochloride. We can call that to be pyridinium hydrochloride. So this is PyHCl. This stands for pyridinium chloride. Pyridinium hydrochloride. That means we have to break the OCH3, either group. The removal of either group is not that much easy. It's not that much easy. We can do that by using this process. Okay, this is the main process. Okay, now this is an important compound. We got the correct structure that we required for this. Okay, now what you have to do is that you have to convert. Okay, this compound. Which compound? This is the benzonitrile compound. We have to convert this benzonitrile compound to our luciferin. To a luciferin. To convert this the compound to luciferin. Okay. Now, what we're going to do is that we already got this compound. We got this compound. Okay. Now we have to convert this compound to our 5-ply luciferin. Okay. We are going to see how we can convert this compound to this compound. It's a very simple process. We just need to react the compound with cysteine. We're going to react the compound with cysteine. The thing is that we're going to react the compound with cysteine. Okay, so it is actually what we're going to do now. Very simple process. This is the compound that we have already synthesized. It's a compound number 12. It's a compound number 12. Okay, this is cysteine. Cysteine is an amino acid that we have discussed. This cysteine is an amino acid with thiol group, sulfur containing amino acid. You have to treat this with sodium, okay, in presence of liquid ammonia. Okay, sodium in presence of liquid ammonia at room temperature. At at room temperature, RT. If it is written RT, that means room temperature. Okay, it's written to room temperature. Okay, so you'll be getting this from room temperature. You'll be getting this in room temperature. What will happen is that you can see that there should be a new ring formation. And there is carbon nitrogen bond here. This nitrogen and this hydrogen and this hydrogen. This will go out as ammonia. Okay. As a result of that, what will be getting is this. Okay, there is OH, there is N, there is sulfur, double bond here, here. Okay, here there is the carbon, this is a carbon, this is a carbon, this carbon. There will be one valency will be satisfied with sulfur atom here. You can see that here the two valencies remaining there, and these two valencies and the valency of the two hydrogen atom removed from the NH2 will be satisfied by the nitrogen. There will be nitrogen. Okay, and you can see that here this is the thing, COH. It is actually what we getting, and it's called the luciferin. It is called the luciferin. Okay, this is the synthesis of luciferin. This is the synthesis of luciferin. Thus, we can get luciferin from para-anisodine. As I told you, this is only the luciferin from the firefly. Okay, so I am restricting my discussion with firefly luciferin. It involves 9 steps. Okay, thank you.